Welcome! In this video, I'll show you how to solve problem 6.9 as it appears in the second and third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem is a very beautiful problem because it allows us to use basically all the machinery that we have learned so far and applied in one single problem. So this problem says, consider a quantum system with just three linearly independent states. The Hamiltonian in matrix form is H is equal to V0 times, well, this matrix, where V0 is a constant and epsilon is some small number. Now, we are going to be working in matrix form, which is often very confusing, but as it turns out, it is very useful, and in fact, it's going to make our life very easy in this problem. So, part A says, write down the eigenvectors and eigenvalues of the unperturbed Hamiltonian, where epsilon is equal to 0. So the unperturbed Hamiltonian, this is V0 times, now with epsilon equal to 0, we get 1, 0, 0, 0, 1, 0, 0, 0, 2. So we want to find the eigenvalues and eigenfunctions, or eigenvectors in this case, of this matrix. But that is very easy because this is already diagonalized. So we don't have to do anything. It's already diagonalized. Whenever we have a diagonalized matrix, its eigenvalues are on the diagonal. So we know already that the eigenvalues are lambda 1 is 1, lambda 2 is also 1, so we have a degenerate case there, and lambda 3 is 2. And the eigenvectors, let's call them, I don't know, chi1 for example. This is 1, 0, 0, right? This one right there. Then we have chi2, which is, okay, that doesn't look good at all, actually. Let me fix that. So it is 1, 0, 0. Then we have 0, 1, 0. And finally, chi3 is 0, 0, 1. Why 1 and not 2? Of course, because they need to be normalized, right? So we took 0, 0, 2 and then we normalized it. So these are our eigenvalues and eigenfunctions. So as you can see, part A, very easy because the matrix is already diagonalized. If it hadn't been, then we would have had to diagonalize it, which is what we will do in part B actually. So that was part A. In part B, it says solve for the exact eigenvalues of H, expand each of them as a power series in epsilon up to second order. So let's now solve this exactly. So part B, our matrix H is 1 minus epsilon 0, 0, 0, 1, epsilon 0, epsilon 2, right? Let me double check. And this is of course multiplied by V0. Let's not forget about it. So V0 times all of this. So let's now find the eigenvalues. How do we find them? Well, to do that, we need to diagonalize. So basically we need to find when is this matrix, right? So V0 times the determinant of 1 minus epsilon minus lambda, right? 0, 0, 0, 1 minus lambda, epsilon, 0, epsilon 2 minus lambda. This determinant has to be equal to 0, right? This comes from our classic equation determinant of our, it's basically this H minus I lambda, I being of course the identity matrix, right? So that's where this comes from, right? We simply subtracted this I lambda. So this, I hope this is not new. This is something that you do have to know how to do at this point. It's very important. So to calculate that determinant, we get V0 times, and now we have 1 minus epsilon minus lambda times, and then we have this times this. So we get 1 minus lambda, 2 minus lambda, minus this product, so minus epsilon squared. And that has to be equal to 0. So that means that for this to be 0, either this part is 0 or that part is 0. So from this part, we get that lambda, well, one of the lambdas, let's call it lambda 1. I don't want it to get confused with the unperturbed ones, but we'll be careful. Lambda 1 is 1 minus epsilon. And from this other part, right, and of course, this is multiplied by V0, so don't forget V0. And from this other part, we have let's see. So let's just multiply through. So we need 1 times 2, so 2 minus, then we have 3 lambda plus lambda squared minus epsilon 0 has to be equal to 0. Or rearranging this, lambda squared minus 3 lambda plus 2 minus epsilon squared has to be equal to 0. So here, applying the quadratic formula, we have that lambda plus or minus is equal to minus b, so 3 plus or minus, and this of course multiplied by v0, right? All of this will be multiplied by v0, 3 plus or minus, and then we have square root of b squared, so 9 minus 4 times a, which is 1, times c, 2 minus epsilon squared, and all of this divided by 2, and all of this multiplied by v0. Okay, so right, the v0, I did plug it in now at the end because it is indeed a factor of this entire thing. I just want to make sure that by the end we keep in mind that there's basically a v0 everywhere here, so we can't just leave it outside. Okay, so here, this is 3 plus or minus square root of 9 minus 8, so 1, and then plus 4 epsilon squared divided by 2. So this is basically, I'm going to do it like this. So all of this factor of v0 divided by 2. So this is our result, but this is where we now want to approximate, because epsilon is very, epsilon is very, very small, which means that the square root, we can approximate it. How do we do that? With the binomial theorem. We have done it a few times before, but just in case, if we have 1 plus x, or maybe in this case 1 plus, no, x, yes, I was going to change notation, but this is okay. So 1 plus x to the 1/2, we can approximate this using the binomial theorem as 1 plus 1/2 times x, and then a lot of other terms, but we don't need them. Why? Because x is 4 times epsilon squared. And this is already epsilon squared, and the next term would be epsilon to the 4th. And that is way too small. That's why we don't need to worry about it. So we can approximate 1 plus x to the 1/2 as 1 plus, and simplifying this, 1 plus 2 epsilon squared. So by using that approximation, we can find lambda plus to be, let's see, v0 over 2 times 3 plus 1 plus 2 epsilon squared, which gives us 2 v0 plus epsilon squared, and lambda minus gives us, in this case, we get v0 minus 1 here, so we get v0 minus epsilon squared, right? Let me double check. So 3 minus 1, we get 2 divided by 2, and then 2 epsilon with a minus. Okay, yes. So here we have the remaining values for lambda that we wanted. And of course, note that if epsilon is 0, right, if we are in the unperturbed case, we immediately get back the cases v0, 2v0, and here we also get v0, which is the same that we had here. Of course, these values 1, 1, and 2 have to be multiplied by v0, right? Because then we have this v0 right there. Okay, there we go. So this was let's see, what was it exactly? So, okay, we found the exact eigenvalues. Now we want to use part C, right? We want to use first and second order non-degenerate perturbation theory to find the approximate eigenvalues for the state that grows out of the non-degenerate eigenvectors of H0. Okay, so that was a mouthful. But basically we want to use first and second order non-degenerate perturbation theory for the state that is non-degenerate. So this one, because we have these two degenerate states, so the state that is related to this, which is of course chi3. So that is what we want to do. So first and second order non-degenerate perturbation theory, of course, because this case is non-degenerate, so there's no point in using degenerate perturbation theory. So first order, how do we do this? Well, the first order correction for this case is going to be, now this is 3 because we are dealing with this third state. This is simply our wave function, which is chi3, sandwiched with our perturbation Hamiltonian. Now, what is everything? Well, this bra is, right, the bra of this, so it is 0, 0, 1. Then we have our matrix H prime, which we have already seen. It is basically this, but only with the epsilons, right? Because let me just make it very clear. H is H0 plus H prime. And if H is 1 minus epsilon 0, 0, 0, 1, epsilon 0, epsilon 2, and H0, as we have seen, is the case when epsilon is 0, then we have 1, 0, 0, 1, 0, 0, 0, 2, 0. And then plus, for this to be the same, we need this to be minus epsilon 0, 0, 0, 1, or rather epsilon and epsilon 0, 0, 0. Right? And of course, all of these are multiplied by V0, V0, and V0. Okay, so this right here is our matrix. So we can factor out epsilon and V0, and we are left with minus 1, 0, 0, 0, 0, 1, 0, 1, 0. And here we can write epsilon V0. And then we have chi3, so 0, 0, 1. You can multiply whatever you want first, these two or these two, whatever. Actually, let's start off with that, actually. So by doing this first, we have product of this times this, which gives us 0, the product of this times this, which gives us 1, and the product of this times this, which gives us 0. And all of this is multiplied with this 0, 0, 1 and epsilon V0. And this, of course, is 0. 0 times 0, 1 times 0, 0 times 1. So there is no first order correction for this non-degenerate state. Now, the second order perturbation theory, this comes, as you might recall, the sum from m equals 1 and 2, right? It goes all the way up to our state. And we have the modulus of the inner product of the other states, right? Chi m with our perturbation Hamiltonian and chi3. The order of these two, of course, doesn't matter. It doesn't matter which one, if you write the m here or there and the 3 here or there. It doesn't matter. And all of this is divided by, I believe, m0. I'm going to double check that because I don't want to make a dumb mistake. That is E3. Yes, so it is E30 minus EM0. This order does matter. So let's find these product, because this is basically the sum of chi1 h prime chi3 squared divided by E30 minus E10 plus the same thing, but now with 2 instead of 1. So E30 minus E20. Let me write it a little bit neater. There we go. So let's now calculate the inner products. So chi1 h prime chi3. This is, let's see, so chi1 is 1, 0, 0. So this would be 1, 0, 0 as a row vector. And then we have our matrix, which is minus 1, 0, 0, 0, 0, 1, 0, 1, 0 times epsilon V0, of course. And then our xi3, which is 1, 0, 0, 1, sorry. So here we multiply. Let's multiply the matrix and the row vector first. So we get minus 1, then this and this we get 0, and this and this we also get 0. So 1 minus 1, 0, 0 times epsilon v0 times 0, 0, 1, but this thing is 0, right? Minus 1 times 0, 0 times 0, 0 times 1. Now let's go for, so of course this entire thing is then 0. We don't need to worry about anything else. Now let's go for chi2 and h prime and chi3. So this thing would be, now it is 0, 1, 0, and the rest is the same. So minus 1, 0, 0, 0, 0, 1, 0, 1, 0, and, well, epsilon v0, 0, 0, 1. So by multiplying these two, we get this times this gives us 0, this times this gives us 0, and the only one that doesn't give us 0 is that last one. So we get 0, 0, 1 times epsilon v0 times 0, 0, 1. So this thing, as you can see, gives us epsilon v0. So let's we have that, but we still need these two energies. So let's plug it in and we'll find them immediately. So we have to square this, epsilon squared v0 squared divided by E3. What is the unperturbed energy of the third state? It is simply this eigenvalue right there. So it is 2v0. So that energy is 2v0, right? How do we know that? Just as a quick reminder, because in unperturbed, in the non-degenerate case, we find the energy as the expectation value. So it's basically simply the expectation value of the Hamiltonian in that particular state. So basically chi3 h chi3, which gives us h33, which is this thing right there, 2 times v0. Okay, so that's where it comes from. Okay, that is of course because the matrix is diagonalized. That is very, very nice. And that's why we found it so easily. Now, the second energy is v0, right? Same argument, right? Because lambda 2 here is simply v0. So that means that here we get one v0 and one of the v0s cancel out and we get epsilon squared v0. So that means that the energy of this state, so E3, is of course E3 unperturbed plus E3 first correction plus E3 second correction. But what are these things? E3 unperturbed is 2v0. The first correction is 0, and the second correction is epsilon squared v0. So basically, if we factor this out, we get v0 factor of 2 plus epsilon squared. Now, what did we find previously? We found precisely that same energy. So that is very, very nice. So that is the result for part C. Now, finally, let's go for part D. So we want to use degenerate, this time, perturbation theory, to find the first order correction to the two initially degenerate eigenvalues, which were, of course, lambda 2 and lambda 1, these ones right there. And we want to compare with the exact results that we found in part B. So how do we apply or degenerate perturbation theory? So the energies, now let me just remind you very quickly of the formula. The energy in the case, so first order correction using degenerate perturbation theory, this is 1/2 of WAA plus WBB plus or minus the square root of WAA minus WBB squared plus 4 WAB squared. Okay, so we need to find each one of those values for each one, for basically our situation. So what is WAA? As a reminder, WAA we had defined as some wave function that we called psi A in this sandwich with our perturbation Hamiltonian. So the question here is, well, what will we define as psi A and psi B, right? Because psi B, of course, is, or WBB is psi B, H prime, psi B, and then we have psi AB, which is psi A, H prime, psi b. So let's call psi a our state psi 2, and or rather perhaps we can go for psi 1 there, and psi b our state psi 2. So that means that psi a, this will be psi 1 h prime psi 1. All right, so what is that? So there we get 1 0 0, our perturbed Hamiltonian, which was epsilon v0 times minus 1 0 0 0 0 1 0 1 0, and then 1 0 0. So by doing this product, what do we get? We get minus 1, so minus 1 0 0 epsilon v0 times 1 0 0. So this is minus epsilon v0. Now psi bb, this is, let's see, so our state now is 0 1 0 epsilon v0, now the same matrix, and then we have 0 1 0. So by multiplying here, let's just put this in the front, times, now when we multiply we get 0 from this product, 0 from this product, and only a non-zero from the last one, and we have to multiply this by 0 1 0, but this is 0. Now WAB, this will be chi1, which is 1 0 0 epsilon v0 minus 1 0 0 0 0 1 0 1 0 and 0 1 0. So from this product we get epsilon v0, and this times this gives us minus 1, and everything else is 0. But this product is also 0. So now, plugging these results into our formula, we know that WBB is 0, and also that other thing is 0. So basically, we get WAA plus or minus, and this thing is 0. So we get WAA squared, the square root of WAA squared, which is WAA. So there are two possibilities, right? Let me just write it like this. So WAA plus or minus WAA. So in the positive case, E plus 1, this will be WAA, which is, let's see, minus epsilon V0. And in the other case, then we get nothing, right? We get simply WAA minus WAEA, which is 0. So these are our corrections. So how do they compare to what we found previously? So before, let's see, we found one of our states to be 1 minus epsilon v0, right? Which is precisely consistent with this, because if we have some state E1, right, this is the unperturbed energies plus the first order correction. The unperturbed energy was v0, this correction is epsilon v0, so we end up with v0 1 minus epsilon. So what's up with the other one? In the other case, you can see that here we get indeed v0 with no first order correction. However, there is a second order correction, but that is not what we can find using first order correction. So up to first order, we do get the correct results, but you can indeed see that there is a second order correction that we were not able to find using this method. So that is the problem. As you can see, we went over basically every single concept in this topic, which is very, very good. This is a very, very good problem to solve, to practice this. So I hope this was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.